So my slides are visible?
Yeah, yes, all good.
Yeah, I am.
Okay. Okay, so we're streaming our recording as a sort of backup plan. Yeah, okay, maybe I can just start real quick with a brief introduction. So first of all, thank you everyone for joining, and in particular, thank you, Shruti, for taking the time and donating a couple of hours of your time to our research seminar. It's really a great pleasure to host you. For those of you who don't know her, Shruti is a senior researcher and MSR, Microsoft Research in Cambridge, and she's done a lot of work the broad security and privacy area, in particular in cloud computing, machine learning, trusted hardware, and her research really focuses on both sort of theoretical and empirical understanding of the threats of private data used in machine learning, and she's been looking at both attacks and defenses. So her work has been published pretty much in all top security and privacy and ML conferences. She's also served in the program committee of these conferences. Before MSR, she got her PhD from NUS in Singapore, where she also received the Dean's Graduate Research Excellence Award for her thesis work. All right, so without further ado, I guess maybe we can make a start. Thank you so much, Shruti. Take it away.
Thanks, Emiliano. Thanks for the great introduction. Hello, everyone. As Emiliano mentioned, I'm Shruti Tople, working in Microsoft Research Cambridge, and it's my pleasure today to talk about our work on use of causal machine learning for privacy. And specifically, I'll talk about causal versus associational learning from a privacy angle. Before we jump, a bit more addition to the background, I'm part of the confidential computing team in Broad at MSR Cambridge here, where we're looking at end-to-end privacy analysis of machine learning pipelines that starts from like data preprocessing, how data is collected, to the deployment phase, the threat model and adversarial settings where the models will be deployed, focusing both on the attack side, like novel realistic settings such as gray box model stealing, reconstruction for NLP models, or property inference in a multi-party setting. That's attack, but that's not what I'll talk about in this work, but I'm happy to discuss that with anyone interested later. This talk, I'll focus more on the defensive side, which is what we call privacy by design solutions, where the goal is to balance both privacy and utility trade-offs. That's the more pressing problem that we have when using machine learning models. And all the content that I'll present today is in collaboration with my great co-authors, both within and outside Microsoft. And these are the list of papers at a high level that I'll be covering in this talk. So the problem is, I think we all know that very well, of membership inference. It is a very severe and important problem where adversary can predict the participation of a record in training a model without even getting access to the white box parameters or weights of the model, just by like querying the model and looking at the output. This becomes a more serious concern, specifically for sensitive applications such as health records, where, let's say, a hospital is training a model for records of HIV patients to predict the disease. And now this model is offered as a service on cloud so that other hospitals can benefit and query this model. But this also allows an adversary to make queries to this model and predict whether a particular record was used for the training, and thus revealing whether they suffered from the disease or not. So these are called as membership inference attacks, first proposed by Shokre et al. In SNP 2017. But after that, several papers have been proposed and looking at different adversarial settings, black box, white box, just access to the labels, and many more. But the problem still remains, and the likely reason for this attack to be possible in each of these settings is boils down to the failure of generalization of these models across different distributions or even from train to test points. This was first shown by Yom et al. In 2018. And now, more recently, it is shown that a subset of samples are more vulnerable to these membership inference attacks as compared to the general population of data set that participates. For example, outliers or rare samples in the training data set, out of distribution points or subgroups. Several recent works have shown, I mean, these are just few papers that I've listed, but these observations are shown in many other papers that it is not uniform, or the susceptibility to membership inference is not equal to every training point. Some points are more vulnerable than others. And these observations have often been shown for associational models, where by associational models, I mean mostly neural networks that learn associations or are shown to pick up spurious features that are more relevant or correlated to the prediction task. This is mostly because of an artifact of the data collection process, how data is collected. Let me explain this with an example that was mentioned in the Sagawa et al. Paper at ICLR, where the task is to predict land birds versus water birds. And what the model does is just picks on the background information, which is land birds are often pictured with land as a background and water birds with water as a background. The model performs well when these spurious features are present. But these features may not be always present in all the samples. For example, there are cases where there might be a water bird but has a land background. Similar observations and examples have been shown, like the models are not able to predict cow with a snow as a background, or camels that do not have desert as background. So it's really this problem with associational models, neural networks that pick on spurious features. And they fail to generalize when these different samples that don't depict these spurious features appear as test data set during inference time. Or if they're a part of the training data set, then these inputs form what we call as the rare samples or outliers. On the other hand, let's look at causal models, because that's what I said. Like in this talk, we'll look from both perspectives. What causal models do is they learn input features that cause the output. For example, in this graph, we can see we have two features such as heart rate and blood pressure that are responsible for causing the output variable Y, which is disease severity. But then there are also other features such as weight, age that are correlated to these causal features. But the good thing about causal features is that they are often exhibited in naturally occurring data. So if you move on to collecting data from a different distribution, the relation of heart rate and blood pressure to the disease severity will still stay the same. And how causal models are trained usually is using a structural causal model that defines the conditional probabilities. And these probabilities between the causal features and the outcomes stay invariant across different distributions. In this talk throughout, when I talk about a causal predictive model, we will see that a prediction model that uses only the causal parents for predicting the outcome Y. I'll also discuss during the experiment discussion where what happens if such a structural causal model is not known for more complex data set in practice, and what can we do there to train a causal model. Okay, so causal learning and privacy, getting to the main point of the topic. Causal models have been shown to improve out of distribution or domain generalization in several recent papers. They have also been shown to be very useful for robustness to adversarial examples. So at least these two lines of areas hint that causal models are better at generalizing or have a much better tolerance towards outliers or rare samples. There are also other applications of causal learning, such as for fairness and explainability, but that is not something that we'll cover in this talk. So looking at these applications of causal learning, we are looking at the problem of, can causal models improve membership privacy? As there has been a lot of literature in connecting that the membership privacy is related to generalization issues, or the more susceptible points are outliers or out of distribution points. So throughout the talk, I'll focus on two main contributions. One is the theoretical results, which is connecting causal models and how they are robust to MI attacks, which is membership inference attacks, as compared to associational models. So that will be the first part of the talk. And the second part of the talk will look at empirical results to validate these claims. First on tabular data set, which is where we can have a true causal structure is known, but then also on more complex image data set where such causal structures are not known, or it's very difficult to identify which pixels essentially will be responsible for output prediction. So moving on to the theoretical contributions, let's see how we can connect causal learning techniques to membership privacy. Okay, so before we jump into our main result, let's come back to why a causal model that's just trained on causal features or parents as variable would have this invariance property or is invariant across different distributions. Let's consider this simple causal graph where you have your outcome variable, which is y, and the causal parents or XPA here represents a set of features that are causal features or causal parents responsible for the prediction of y. And then there are other features that are connected that can be the children variable of y or other correlated features such as XXSO that are correlated to the parents. The interesting property is that if you intervene, the hammer here denotes intervention or manipulation of any variable for that particular data record, then it does not affect the distribution of the relation of the X parents and Y. Like if you're changing age in the previous example that I showed, changing age will not affect how blood pressure and disease severity are affected. So essentially, the non-causal or spurious features can change their distribution, but the relation between causal features and parents will not change. Thus allowing us this property that the probability of Y given its parents is invariant across different distributions, unless, of course, there is a change in the true generating process for Y itself. Like if there is a natural shift in distribution for the causal features, then the model will have to be trained again specifically to pick on those features. But as long as the true generating process stays the same, like for images example, the land birds, the features of the land birds or water birds stays the same, the model should be able to perform well. Okay, now we have this invariance property understood, and we are ready to compare the generalization property of causal versus an associational model. So we can first, before actually comparing how these two models will perform on different distributions, let's start with in-distribution error, which is our standard loss expectation over points, like test points that are from the same distribution. And then we define another term, which is the out of distribution error, which is the expected loss of the model on points that are from a different distribution. This is P star here. The only condition that we have, which we have assumed or which we have rationalized already, is that the distribution P star of Y given its parents will be the same as compared to what we have in the distribution, the current distribution, which is P of Y given XPA. So once we have this two terms defined, the out of distribution error for a causal model now can be bounded by the in-distribution error and this discrepancy distance term, which is the distance between the two distributions that we want to compute the error for, which is P and P star. But for associational model, the bound has one additional term, like it has this in-distribution error, the discrepancy distance, but there is also this last term, which is the loss of the optimal model on the original distribution to a different distribution. And this term appears because for associational models, as there is no assumption that Y given X, like all the features will stay the same. Any change in distribution in the non-causal features will now result in a new optimal. So the optimal HA on P is not always optimal on P star because the distribution of non-causal features will change. And this gives us that the maximum or the worst case out of distribution error bound for a causal model will always be lower or equal to that of an associational model because of the additional loss term. Okay, so that's what we have established with respect to the generalization, out of distribution generalization property of causal and associational models, which allows us to talk about another important property, which is the sensitivity analysis of a model. As better generalization also leads to benefit in sensitivity of a learning mechanism. And what do we mean by sensitivity? Sensitivity can be defined as the change in the output, which is the model parameters here, when a single point is changed in the training data set. So we have S and S prime, we call them the neighboring data set, and they only differ by this one point, which is drawn from a different distribution, so that the spurious features change or the non-causal features change, but the true causal features responsible for the outcome, they remain the same. And since we've seen that the optimal causal model is the same across all the distributions, because the optimal causal model just relies on picking on the causal features and they don't change. This additional new input that is used during training will have lesser impact on the trained causal model as compared to an associational model, which will also see that it has some different spurious features or background features, and the model needs to learn from them. So this establishes that the sensitivity or the change in the output for a causal model is lower on two neighboring data sets as compared to an associational model when trained on the same two neighboring data sets. Okay, and it's natural that once we've talked about sensitivity, it allows us to easily talk about the most important privacy property, which is the differential privacy guarantee, where what differential privacy just is that for any mechanism to satisfy epsilon differential privacy, the ability for an attacker to distinguish between the output when trained on neighboring datasets, S and S prime, should be small, and it is essentially bounded by this term epsilon, which is also the privacy budget. So smaller the epsilon, better the privacy guarantees. Like for an epsilon of 0, the attacker will not be able to distinguish the outputs at all. And this epsilon, again, is calibrated by computing the sensitivity of the model. So how differential private mechanisms work is you add noise to your output based on the sensitivity of the function. You first compute sensitivity of the function and then add corresponding noise. So the lower the sensitivity, lower is the noise that you'll have to add, and a better epsilon guarantees is what you'll get. So with this, we have our first main result, which is when equivalent noise is added and models are trained on the same data set, a causal mechanism will provide an epsilon C differential privacy guarantee, which is less than or equal to that for an associational model, which will give you an epsilon A differential privacy guarantee. And lastly, when talking about membership inference attack resilience, we have like the literature has defined advantage of a MI adversary as true positive rate of predicting members versus minus the false positive rate. And it can now be bounded by the epsilon that we saw before for differential privacy. These bounds were first shown by Yom et al., but now we have much improved bounds shown recently by Erlingson et al. And Humphreys et al., where you can get much tighter bounds by having epsilon for your machine learning models. But irrespective of whatever bound we take, now that we've established that an epsilon for a causal model will be lower, we can then have this result that when trained on the same dataset size n, the membership advantage of a causal model is lower than that of an associational model. And because the optimal causal model is the same across the different distributions, we can prove a stronger result, which is when your training size tends to infinity, like you have infinitely large number of training points, the membership advantage of a causal model actually tends to 0, because an attacker will not be able to distinguish the points that are from one distribution versus the other, as the model will behave exactly the same. Okay, so this is the theoretical part. I know it was a bit too much, but I have this summary slide which I really like. So there is a very neat trend with respect to why causal learning mechanisms are better for membership inference. We started with looking at the key property of causal models, which is the invariance property, that the causal features remain invariant across different distributions. That allows us to justify the better generalization property of causal models, which eventually allows us to argue about why are causal models lower in sensitivity, like the change in the output is lower because they can generalize better. Sensitivity leading to stronger differential privacy guarantees, because now you'll have to add less noise to hide the distinction because of the contribution of a single sample, and leading to more resilience to membership inference attack, because the MI advantage of an attacker is bounded by the epsilon guarantees that you have. Okay, so this concludes the first part of the talk. If there are any questions, I am happy to take at this point. Else, we can move on to the more fun part or the empirical part, where we get to see numbers and graphs. Okay, I can continue with the empirical contributions, where we are looking at two possibilities. One, where the true causal graph is known for tabular data set, where it's much easier, and researchers have looked at different interventions to identify what would the true causal graph look like. But we're also looking at more complex settings or more practical settings where the true causal graph is unknown. For example, for image data set, where it's difficult to really pinpoint what will be causal features that are responsible for a particular output prediction. Okay, so for the known causal graph setting, as I said, we're looking at tabular data set. This graph on the right shows results for child data set, where the outcome variable is X-ray report, having 5 possible values for X-ray report. And the non-causal features are what differ in between P and P star. So the graph shows the attack accuracy on y-axis and the total data set size used for target model. As we can see, for lower data set sizes, even a causal model has significant attack accuracy on P star, which is for training points that are outliers or out of distribution. But as the model converges and has learned the true causal features at around 100K points, the attack accuracy for a causal model is close to random, 50%. But the same for a associational, or what we call, we use the DNN here, the 3-layer network, that increased to 80%. So a neural network actually that learns spurious features was allowed distinction of these points from an out of distribution P star to predict much more accurately as compared to a causal model. This was just in a black box setting looking at confidence predictions. So the confidence predictions of the DNN on P and P star was much different as compared to the causal model that just relied its based its prediction on the causal features, which did not change across distributions.
And, hi, Shruti. Sorry, I have a question here.
Yeah.
So you mentioned that here your tabular data set, your causal graph is known. Yeah. So yeah. This how I mean, this causal graph is a part of the data set that people summarize it over domain knowledge, or use some other algorithms to automatically find this causal graph.
So what this data set is specifically where the causal graph is outlined. Okay. And the conditional probabilities are known, but you raised a good point. There are also many causal discovery algorithms that just take in observed data and then you can generate a causal graph from it. So those algorithms actually look at discovering by doing manipulations or interventions on each of the variables to identify what a true causal graph will look like. But we did, because this was the first work and we were just trying to do some synthetic evaluation, we chose a causal graph and then change the probabilities to create this different distribution, which is P star.
All right, great, thanks.
Yeah, and just looking at the utility of the models, like of course, we've seen that causal models, both theoretically and empirically with this result, are better for privacy. But when plotting for utility, we also see that causal models perform, at least for this data set, as good as DNN models, giving the same utility on both in distribution and out of distribution points. So better privacy without loss in utility. We also did a small ablation study to really understand the impact of noise added to the non-causal features. So the x-axis is the amount of noise added, and y-axis the attack accuracy. And by noise, I mean what we did was just change the conditional probability distribution of non-causal features related to y, and kept those for the causal features the same as the original distribution. As you can see, the more noise is added, or the further the point goes from the training distribution or the majority distribution, the higher is the susceptibility to MI attacks with associational models. But for causal model, as you can see, the attack accuracy just stays around random, which is 50%. This is just showing that we did an extensive evaluation on different data sets with having different number of nodes in their causal graph. So extensive as like I think water had 100 to 200 nodes, where all of them show consistent result that they have high attack accuracy for the associational model when the P star or a different distribution had added uniform noise to the non-causal features. But they gave same classification accuracy between causal and associational models. So the model on the graph on the right shows that the prediction accuracy stays the same. Again, showing better utility with privacy. Okay, so this was the synthetic setting, or where we know what the true causal graph is and we could manipulate the non-causal features. But we also studied the setting where the causal graph is not known. And how would you train a causal model in this case? There is a line of work which can be categorized as invariant representation learning algorithms. So the goal of these algorithms is to learn a representation that would stay invariant across different environments or across different domains, distributions, whatever is the task. So the first paper on this was using colored MNIST as a data set, where color is a spurious feature. It's just a binary classification task where you want to predict if a digit is less than 5 or more than 5. Less than 5 are, I think, labeled green, and more than 5 are labeled red, with some noise added as well. So you'll see some digits are colored differently than what the task is. But the idea is that if the model uses color as a feature to predict the output, whether the digit is small or less, then it's doing the wrong thing. Whether it should actually predict based on the digit itself. So we used IRM, which is the invariant risk minimization approach, as a causal model for us to learn the same task, and an associational model, which is just the standard ERM, to train and predict the same task. And what we saw was that even in this setting, the causal model gave us attack accuracy close to a random guess, and the associational model was much more susceptible to MI attacks. So this is a simple setting, binary classification, where color was a spurious features. We extended this to a bit more complex setting where you have now multiple domains where the angle of the digit, rotation of the digit is the spurious feature. And the model may have to predict it on unseen domains, such as rotations that the model has not seen during training. And how will membership inference attack accuracy performed when these models are trained specifically with the goal to learn invariant representation across different domains. So for the graph on the right, the associational models are the first two, which is ERM, empirical risk minimizer, and random match, where it's just trying to learn invariant representations for random images belonging to the same class. So it does not really take into consideration if two images have the same causal features. It's just the class label is taken as a way to match the input images. And causal models can be considered to be those that actually are trying to learn some causal features or invariant features responsible for predicting the output irrespective of the domain. So the angle rotation is not really what the model should be learning on. So match DG and perfect match are the ones that match for optimizing for causal features. Then there are other approaches like CSD and IRM that have a similar strategy of learning invariant representations that take into consideration the inputs from different rotation domains that are provided. And even for those, we can see that, there are multiple results from this graph that we can see. First, let's look at the attack accuracy for domains 2 and 3. So when out of the 5 that are shown on the left, only 2 domains are provided to the training algorithm. And here we can see that ERM and random match, like the associational models, have slightly higher attack accuracy, and the other models the causal models have lower attack accuracy, with some exception where maybe the algorithm is not doing well on the task itself. The theory holds, but the empirical implementation does not hold true. But the perfect match algorithm, which we have shown is good at capturing causal features and is useful for prediction accuracy, does really well and has lower attack accuracy. But as you go to higher number of domains, like 5 domains, even ERM can do better. In a way, what this is saying is the empirical risk minimizer or associational models are also able to capture causal features if you provide a diverse data set. Again, this relates to many results that have been shown in the literature, where if you just given more data set or more features, then associational models can perform well as well. But random match, which is not really designed to capture causal features, again performs poorly with respect to MI attack accuracy. And perfect match, which is close to the true causal model that we would have for this setting, has a really low attack accuracy. So this is a relative comparison. This doesn't show that causal model is perfectly private and always has random guess close to 50%, but it does perform well as compared to an associational model that would learn more spurious features and less causal features than the true causal model. And lastly, because we've shown that causality with differential privacy provides better epsilon guarantees, to empirically evaluate it, what we did was train a causal and an associational model to achieve the same epsilon guarantees and looked at the utility of those models. And as you can see from the graph, for the same epsilon DP guarantee, like for epsilon of 1, the causal model is able to predict accuracy of more than 80%. And that for the associational model, ERM, it's way less than 75%. So the true prediction accuracy of this model without any addition of noise reaches around 99% for both the cases, like for ERM or perfect match. So this is like in this prediction accuracy. But when you're adding noise for an epsilon of 1, especially with these invariant feature learning techniques, the results do provide a larger gap between the utility of ERM and causal model, is showing that causal models are really a way to balance the privacy utility trade-off. Okay, I think this is the last slide. And to conclude, we've looked at 2 different contributions. One is from the theoretical point of view, where this was the first work to connect causal learning algorithms to differential privacy guarantees and eventually their resilience to membership inference attack, which is a severe privacy concern. And we also looked at empirical results for both the cases where the causal graph is known or not known. And the code is available on the repository RobustDG to reproduce the results. I think with this talk, I really want to encourage that causal learning techniques are a promise or a way ahead to balance privacy utility trade-off. We've seen causal learning techniques useful for many other domains like robustness, adversarial examples. But from the privacy angle, I think the exploration or the results out there are not yet as to the other areas such as out of distribution generalization, for example. So we need more research in this direction, and this work definitely shows that there is promise and the results are good with respect to balancing privacy utility trade-off. Yep. Thank you, and I'm happy to take questions if any.
All right, I think Emiliano is probably still busy for his things. Any questions here?
Hello.
Okay.
Thanks for the great talk. So I had a question. So here you consider the membership inference attack, right? So what the other types of attacks have you looked at?
So yeah, that's a good question. We've actually looked at attribute inference attacks as well. So the one paper that I have cited, I think there are small set of experiments, and we saw that causal learning can also be useful for defending against attribute inference or property inference attacks, just because if what you're trying to infer in terms of the attribute or property is a non-causal feature, for example, a sensitive variable such as age or weight, which is not relevant for the output prediction task, then causal models can be useful to hide that information, which is what associational models will leak. But of course, if your task itself is using those features as causal features and they are responsible for the output prediction, then you will not be able to mitigate attribute inference attacks against those features. So they are useful in settings to protect against or mitigate against attribute inference of non-causal features.
Thank you.
All right, I got another question. Yes, I got another question myself. So you mentioned that the causal learning is also, effective against, increase the robustness of the model against those examples. But how about, because I think that there are papers show that the membership inference and those examples are somehow sort of a negative correlation. Like if you have a better membership inference, probably those example is harder, or something like this. So would this mean that causal learning actually, because this learning paradigm is completely different from, let's say, train a CNN or whatever things. So this is a third space that is be able to reduce almost all kinds of attacks.
I will not go there and say that it can reduce all types of attacks, because there might be something, but it does seem, as for attribute inference, like there are cases where it cannot predict, because if what those attacks are trying to infer is actually a functionality or required for the prediction task, then it's really privacy utility trade-off where you cannot get good utility by reducing. But what associational models in general do is they learn much more information just because of over parameterization or the ability to memorize. And the optimization is, there's only one objective: to get good accuracy on the output task. Whereas causal learning, they're also trained with the objective to learn causal features or invariant features across environments. So this additional property does seem promising, where adversarial examples are also like small perturbations to your original input. And if those perturbations correspond to spurious features, then they won't affect the causal model, but they affect the non-causal or associational models because they're very sensitive with respect to alterations to these non-causal or spurious features. So that's where at least the previous papers on robustness to adversarial examples, that's the property that they've used and shown results. But it'll be interesting to see how the results from the security community showing membership inference and adversarial examples are at odds, and these results, how they can connect.
Georgia.
As well. Yeah, thank you, Shruti. It was a great talk. Thank you so much. I just wanted to ask you, so you mentioned that for tabular data, so your first goal was there, just like assuming the causal graph. But then you mentioned that there are other models that you can infer the graph. Just wanted to ask you if you have made that other step of, let's say, running privately the causal graph, maybe like spending some privacy of some budget of your privacy there, and then running the model in a DP way as well. And if this is tricky, yeah, I just wanted to ask you this.
Yes, it is tricky. And we have done some work in that direction. it's easier if your causal discovery is integrated with your learning task as well. Then it's just about like changing your optimizer to add noise in both the settings where the data is learned. Like the causal graph is learned from the data, and then you're doing the prediction task. But if those are distinct, then I would still think that the composition property should apply. But I have not looked at cases where the causal graph is discovered from a different algorithm, and then the generated data from this causal graph is used to train a different learning task.